We now discuss the solution of a problem from the section Linear Algebra, and the problem is on the inner product. And this question has appeared in CSIR National Eligibility Test held on 16th February 2022, and this question is from the section B. The problem is, let n greater than 1 be a fixed natural number. Which of the following is an inner product on the vector space of n by n real symmetric matrices? We are given four options. Option 1, bracket a comma b is equal to trace of a multiplied by trace of b. Option 2, bracket a comma b is equal to trace of ab. Option 3, bracket a comma b is equal to determinant ab. Now, option 3, bracket a comma b is equal to trace of a plus trace of b. Now, we have n is a fixed natural number greater than 1. We have the vector space of all n by n real symmetric matrices over the real field. And here are the brackets are given, bracket a comma b. We will call it as the inner product of a comma b unless and until it qualifies all the properties of the inner product. So we have to decide which one of the following defines an inner product. Let's recall the definition of the inner product. Let V be a vector space over a field F. The field F is either field of real numbers or the field of complex numbers. A map that assigns for each ordered pair u comma v. For each ordered pair of vectors u comma v in V, we associate a scalar from F written as bracket u comma v. That will be called an inner product if it satisfies the following properties. That is, for each ordered pair u comma v belongs to V cross V, we associate a scalar F, and that is denoted by the bracket u comma v. That is called an inner product if it satisfies the following properties. Property 1, bracket u comma v is equal to bracket v comma u for all u v belongs to V. If F is the field of real numbers, it is called the symmetry property. And if F is the field of complex numbers, bracket u comma v is equal to the complex conjugate of bracket v comma u, true for all u v belongs to V, then it is called conjugate symmetry. Second property, bracket alpha u comma v is equal to alpha times bracket u comma v for all u v belongs to V, for all alpha belongs to F. It is called the homogeneity of the inner product. Third property, bracket u plus v comma w is equal to bracket u comma w plus bracket v comma w for all u v w belongs to V. It is called additive property. And these property 2 and property 3 together is linearity in the first slot here. If alpha is here, it will be alpha bar. So that is why it is called in the first slot, linearity in the first slot. The fourth property, the positivity, that is the bracket of v comma v is greater than or equal to 0 for all v belongs to V. And the fifth property is the positive definiteness, that is bracket v comma v is equal to 0 if and only if V is the 0 vector. And many a times, satisfying this fifth postulate, fifth property, in many cases it fails. And in many examples, we normally test this to IP4 and IP5. Okay, we continue. And we have n is a natural number n greater than 1. We have V, the vector space of all n by n real symmetric matrices over the real field. And we eliminate the some of the options, 3 options, by giving some counter examples. Let A is equal to Aij n by n. We are taking a n by n situation. You can also try 2 by 2 situations also. The same examples will work out if we put n is equal to 2. But anyway, I have taken n by n matrix where Aij is equal to A11 is 1 and A22 is minus 1, and the other Aij's are all 0 otherwise, other than these two. The remaining elements are all 0. So clearly A is not a 0 matrix. The matrix A, the n by n matrix, what I am talking is this one. Now A belongs to V because A is a real symmetric matrix, right? A transpose is equal to A. And observe trace of A is the sum of the diagonal entries, that is 0. And let us take the option 1. The bracket A comma B is equal to trace of A into trace of B. We test the positive definiteness. Assume that this defines an inner product on V. So the bracket A comma A is equal to trace of A into trace of A. In the place of B we have taken A, and trace of A is 0, 0 into 0, 0, but A is not a 0 matrix. This contradicts the positive definiteness property of the inner product. So the option 1 is not an inner product on V. Thus we have eliminated the option 1. We take the same example, and we take the option 4. Bracket of A comma B is equal to trace of A plus trace of B. Assume that this defines an inner product. We take the bracket A comma A is equal to trace of A plus trace of A. In the place of B we have A. 0 plus 0 is 0, but A is not a 0 matrix. So this contradicts the positive definiteness property of the inner product. Therefore, the option 4 is not an inner product on V. Now we consider another example. Let A is equal to Aij, n by n matrix, where Aij is defined as A11 is 1 and the remaining Aij's are all 0. So clearly A is not a 0 matrix. And the matrix, the n by n matrix, what I am talking about is this one. Now A belongs to V because it is a real symmetric matrix and its determinant is obviously 0. Now take the option 3. The bracket A comma B is equal to determinant of AB. Assume that this defines an inner product on V. Bracket of A comma A is equal to determinant of A into A. By definition, by this, that is equal to determinant of A into determinant of A. Determinant of A is equal to 0. So bracket of A comma A is 0, but A is not a 0 matrix. This contradicts the positive definiteness property of the inner product. Therefore, the option 3 is not an inner product on V. So we obviously conclude the option 2, that is bracket A comma B is equal to trace of AB, is an inner product on V. Therefore, the inner product of A comma B is equal to trace of AB is an inner product on V. Now, notice that the inference what we have drawn, that the option 2 is true, by the elimination process. That is the other options, option 1, 3 and 4 are not true, and therefore the option 2 is true, because only one true statement will be there in the section B, and we have drawn such kind of an elimination. But the proof is needed for this. For a detailed proof of this result, please see the next video. In that, I have shown that this defines, that is the bracket of A comma B is equal to trace of AB, defines an inner product on the vector space of all n by n real symmetric matrices over the real field F. So that is the discussion of the solution of the problem from the section Linear Algebra, and it is a problem on inner product. I am sure that you have understood the solution of this problem, and quite a good number of times problems are coming on inner product. The verification of the inner product, it is coming. So go on working out some more examples on inner product. I wish you all the best. Thank you.